Let us look at the concept of matching and how far we can match this concept with the biostratigraphic correlation. Consider the vertices S1, S2, S3. At one side I have written, and at the other side P1, P2, P3, P4 and P5. Note that S1, S2, S3, none of them are having a common edge, and none of these P1, P2, P3, P4, P5 have got common edge, and some of the SI, that means either S1, S2 or S3, are joined with some of the PI through the edges. Such a graph is known as a bipartite graph. Here G, which is this graph, can be considered to have two disjoint set of vertices. SI is one, another is PI. So, if we remove the edges between SI and PI, all the edges will be gone, and as I said, no SI are mutually connected, and so also the PI. Geological correlation. What happens at one side within the lithology, A, B and C, maybe by biostratigraphic means we have correlated with A dash, B dash and C dash. This is the P1 section and this is the P2 section. What is the basic difference in this kind of bipartite graph and what I have drawn over here? Here at one side S1 is linked with both P1 and P5, which is not the case in biostratigraphic or in any geological correlation. A portion is uniquely correlated with another portion, and A is not correlated with B dash or C dash, B is not correlated with A dash and C dash, C is not correlated with A dash and B dash. Concept of matching. A matching in a graph is a subset of edges. Note this, subset of edges. There are many edges in a graph and few of them will be considered as a subset, and that will be called as matching. In the definition of matching, there will be no vertices, only a few edges. What kind of edges? In which no two edges are adjacent to one another, that is, no two edges have a common vertex. Now, we look at this graph and we can see the edges are already marked, and those edges are E1, E2, E3, E4, E5, E6, E7 and E8. So, this is the master set, and within that if I pick up few of them, E1, E4 and E7. So, if I mark by black color E1, E4 and E7. In these edges there are no common vertices. That means these edges have, no two edges have a common vertex. So, in that case M1 is called a matching. Now, we take E8 and E6. Where are they? This is E8 and this is E6. What happens? There is no common vertex between them. So, therefore, E8, E6 will be a subset of edges, and we call this M2 as a matching. Now, this concept matching can work for the stratigraphic correlation. We can see that the edges A, B and C, A, B and C is a matching. We can call this by the set M0 is a matching. Why? Because A, B and C do not have common vertices. So, our stratigraphic correlation actually is matching. Now, imagine that the resolution of correlation is increased. Earlier we were linking B with B dash, but now there are several horizons B1, B2, B3 defined, and in this side B1 dash, B2 dash and B3 dash, and now they have been correlated. So, in this case still it is a bipartite graph and still it is a matching. Suppose I want to delete the vertex B. If we delete a vertex from S, this is the S side, Si, and this is our Pi side. If we delete a single vertex from either Si or Pi, what happens? it is excluded, and also it excludes another vertex from Pi or Si on the other side and an edge. This is going to happen. Why we should delete this vertex? Suppose we find that this connection BB dash edge, by further studies we find is not correct. So, to avoid that, sometimes we have to delete the edge. We will come across a term known as the maximal matching. It is a matching in which no edges in the graph can be added. In this case, if I write AA1, B1, B1 dash as a matching, in this subset I can also add other edges. For example, or I can think of another matching with more number of elements in the set, such as AA1, B1, B1 dash, B2, B2 dash, B3, B3 dash, C, C dash. Now, this is the matching with maximum number of element, and this will be called as the maximal matching. So, in one of our previous examples, here E1, E4, E7, I cannot add another vertex. So, these are already there within the set, I cannot add any single one. So, therefore, this is a maximal matching. I cannot add another edge. So, this is called a maximal matching. Now, let us look at E8 and E6. We can see easily that there can be more than one maximal matching in a single graph. Let us take this triangular graph with edges C0, B0 and A0. Now, the every single edge in this case is a maximal matching. For example, if I take this A0, I cannot think of any other edge within the graph without common vertex either here or over there. Similarly, B0 and C0 are the maximal matching. So, this is an example where a single graph with 3 maximal matching. Let us look at the maximum matching right now. It is a kind of a maximal matching with the largest number of edges. So, while defining the maximal matching, we have chosen the edges with highest number of elements. All those sets will be compared, and the one with largest number of edges will be called maximum matching. Let us take this example. I have drawn a rectangle and a diagonal, and the edges are marked by A, B, C, D and E. Now, we can see A comma C, this is a maximum matching. Why? Because if I take A and C, I cannot think of any other edge without a common vertex that are for A and C, and E on the other side is another maximal matching. Now, between these two, which one is maximum matching? This one. So, be careful with the term here, it is maximum, and what I was talking earlier is maximal. Now, let us look at the matching number, the definition. The cardinal number of maximum matching, that means the maximum matching has got so many elements, count them and write down. So, in our previous case, we can see this is the maximum matching A comma C, and there are 2 elements. So, I can write it to be 2. So, in other words, the matching number for this graph is equal to 2. Now, let us look at a perfect matching. If every vertex of the graph is the n vertex of some edge. For example, every vertex is touching with the edge with some other vertex. So, in this particular stratigraphic case, what is the maximum matching? Easily we can say all these lines I can write down AA dash, BB dash and CC dash. Therefore, the matching number in this case will be equal to 3. Let us look at this particular situation. We are dealing with P1 and P2 stratigraphic sections, and there are horizons at M, A, B, C, D, and on P1 and on P2 it is P, A dash, B dash, X and W. Now, note that I cannot assign M with P because of insufficient data. This data can be paleontologic data for a biostratigraphic correlation, it can be lithologic data for lithostratigraphic correlation, it can be chemical data for a chemostratigraphic correlation. Similarly, C, I do not know whether it goes with W and X, so the matching has not been done. So, it is not a perfect matching in this case because some points are not connected by the vertices. Again, let us look at the definition of perfect matching. If every vertex of the graph is the n vertex of some edge, M is not the n vertex of some edge. Okay. Now, I draw this graph, and here the edge subset A, G and D Where is A? This is A, this is G and this is D. Only the 3 edges I have given some symbol A, G and D, others I have not given because we are not discussing about them. This constitutes a perfect matching. You cannot bring any other edge which is not connecting these points or the nodes. Every perfect matching is a maximum matching, but not the vice versa. So, draw such a case as your exercise. You must do these small exercises that I keep on giving you once a while. I will come to an issue of marriage problem. This is the term that I have not chosen. In mathematics, it is defined like that. Consider the boyfriends x1, x2, x3 and x4, and there are girlfriends. x1 has got y2, y3, y4, x2 has got y2 and y4, x3 has got y1, y4, y5 and x4 has got y1. And the marriage problem is that find out a match that each boy marries his girlfriend, and of course a single marriage is permitted. I mean, between one boy and one girl will be one marriage, and one boy cannot marry more than one girl or vice versa. So, first of all, we create a bipartite graph. We can see x1, x2, x3, x4 written over here, and then y1, y2, y3, y4 and y5 is written over there. The first observation is that this set, the cardinal number is 4, and here in this set the cardinal number is equal to 5. So, with the condition that we have set, of course, which means that there will be one girl who will remain unmarried, or correlation or matching will not be possible to do for her. There can be other examples set. There are a few teachers in a school and there are few subjects to be taught. One teacher can teach more than one subject, so you can write a column of teachers T1, T2, T3 and subjects S1, S2, S3, and you can create a bipartite graph. Now, another example is students who opt for different dissertation topics. This is a common in colleges and universities. We have, let us say, 4 students. So, S1, S2, S3, S4, and the dissertation topics floated by professors are D1, D2, D3, D4, D5, D6. Now, all the students are asked for their first preference and second preference, and then the graph can be constructed. In this particular case, what I am talking, there will be edges connecting students and the dissertation topics, but then there are preferences, first preference, second preference. Whereas, in this graph what I have drawn, there is no such thing. That means, boyfriend x1 has equal preference for y2, y3 and y4. Now, again this may not be the case. So, the bipartite graph or the marriage problem can further be improved based on the preference as well. Now, let us look at the edge subset for this graph. For this graph, we are going to write the edge subset. A1 is x1, y2, x1, y3 and x1, y4. That means, x1 can be linked with y2, y3 and y4. So, what is the subscript here? 1 has gone over there. Now, similarly, this 2 subscript comes over here and over here, and x2 can be linked with y2, x2 can be linked with y4. This is the meaning of the edge subset for this graph. A3, 3 is over here, 3 is over here and 3 is over here. X3 can be linked with y1, y4 or y5. A4, this 4 is over here, x4 can be linked with y1. Now, this matching is called system of distinct representatives of the family of finite sets A1, A2, A3 and A4. I may not enter into its detail, but the interested students can look into it and see in what way in biostratigraphy this concept can be added up. I leave up to you. We will try to understand marriage condition. Here we are taking 3 vertices x1, x2, x3 and the vertices y1, y2, y3. xi are not mutually connected, yi are not mutually connected. So, it is a bipartite graph, and we are going to do a matching so that primarily the x1, x2, x3 group will be satisfied. So, what are the groups? This one is V1 and I have written, and this one is V2 set which I have given. Here we have got 3 elements in the set, and here we have got 3 elements. That means, once the matching is done, there will be no unmatched xi left and no unmatched yi left. Here we are dealing with less number of vertices for easy example, but one can deal with large data set. Now, we will consider the S different possible sets has to be constructed with xi. So, one possibility subset is x1, next can be x2, the next can be x3, then x1 and x2 together, and then x1 and x3 together, then x2 and x3, and x1, x2, x3. In all possible combinations, we have kept them as separate sets. Similarly, now we are going to create as per S the T column. What is that? x1 is connected with y1 and y2. We can see that within the given graph, x1 is connected with y1 and y2 and no other y vertices such as y3. So, that is why I wrote here y1, y2. Now, let us look at x2. x2 is connected with y2 and y3, y2 and y3, that is why it is written. Now, you find out rest of them. x3 connected with y1, x1 and x2 together will be all y1, y2 and y3. x1 connected with some edges, x3 connected with some edges, write them all y1, y2. So, x2, x3 will be y2, y3 and x1, x2, x3 will be y1, y2, y3, because in the graph I can clearly see there is no unconnected edges. So, I will expect if I write all the xi, I will get all the yi over here. Now, we will write down how many elements are there in the set. Here we have only one element, here we have one element, here we have got one element, it has got two elements, this has got two elements, this has got two elements and this has got three elements. Now, I look at the NT, this has got two elements, this has got two elements, it has got one element, this has got three elements, this has got two elements, this has got two elements and that has got three elements. Now, if this condition is satisfied, then we say that the marriage condition is satisfied. That means, every vertex in xi can be linked with yi without any problem. Ns less than or equal to nt. Let us give an example. In this particular case, we can see 1 less than 2. So, the condition is satisfied. Same over here, 1 and 1. So, ns equal to nt is satisfied, 2 and 3 satisfied, 2 and 2, 2 and 2, 3 and 3. So, this condition is satisfied. Therefore, we say that the marriage condition is satisfied. Now, let us look at the geological correlation. Here, we have got the vertices small a, small b, small c, and in the other succession we have the vertices capital A, B and C. PQR is a maximal matching and also a maximum matching, and here in PQR is equal to 3 is the matching number. Now, does this make a marriage condition? What is the marriage condition? Already discussed, and then this condition has to be satisfied. Now, let us start. Consider the V1 set of vertices A, B, C and the V2 set of vertices A, B, C. Now, we will create the S column. So, A, B, C, then A and B together, B and C together, C and A together, and then all of them taken together A, B, C. Now, T we will construct. A is connected with how many vertices in the stratigraphic column? Only A. B with B, C with C, small a small b with capital A capital B, small b small c with capital B capital C, small c small a with capital C capital A, small a small b small c with capital A capital B capital C. NS, the number of elements in the set, here it is 1, here it is 1, here it is 1, here it is 2, here it is 2, here it is 2 and here it is 3. Now, NT, A single element, B 1, C 1, AB 2, BC 2, CA 2 and ABC 3. So, now here we see that NS less than or equal to NT is satisfied, and this is a specific case when we are basically dealing with NS equal to NT. So, NS equal to NT situation will arise whenever we have a geological correlation of this sort, whatever be the number of vertices. All vertices here are linked with all vertices there, and whatever be the number of vertices, then we get NS equal to NT condition. So, marriage condition is satisfied. If we take V1 as ABC and V2 set as small a, small b, small c, same inference can be drawn. How it will work, I am showing you. Here we wrote small abc etc., but here now we will write S as A, B, etc. And here we will write T small a, small b, etc. And we will eventually see that the same condition is satisfied, Ns equal to Nt. Now, let us look at it in a bit different way. In the succession P1, there is a succession P2. A and B are the two vertices that are to be linked, and geologist has linked with small a, small b, small c got escaped. Here capital S will be given by a column A, B and AB together, and T will be given by A connects with A, B connects with B, A comma B connects with A comma B. So, here Ns is equal to 1, 1 and 2, and here it is 1, 1 and 2. So, which means this condition is satisfied, and again in fact this is satisfied. This is a case where each vertex in V1, this is the V1 and that is the V2, can be linked with unique vertices in V2. Now, I take another example here. Now, the left hand side it is P1 and here is a P2. Here we have one vertex which is not matched with the any vertex in the P2. M is not yet correlated because of paucity of the data or some controversy. Now, in this case, show this relation, I mean construct the S column, construct the T column. Similarly, take the case that there are two sections which are barren, no fossils found, no correlation has been made, no correlation and no vertices defined. Then what will happen? In the next phase, you add up, even though they look like simple exercises, we must know there are 2 points where data are there. Here is one point where data is found, but the information is there, but no correlation has been possible. Similarly, take another example where some correlations made and there are a few which are uncorrelated, just like the previous one. Is this condition satisfied? Take another case where there are two vertices here and no vertices here, it is a null set, and then that is why it is barren. What happens to this relation? Are you at all going to construct the T table? That is the question. Let us define a clique. It is a subset of vertices of an undirected graph. That means a graph which is not a digraph or directed graph, a graph without any arrows, such that every two vertices in the clique are adjacent. So, this is a graph G. Name these vertices 1, 2, 3, 4 and 5, and here take these 3 vertices and they are adjacent because they share common vertex. So, also over here this is another case, a subset of vertices 2, 3, 5 and 4, they are adjacent to each other. So, for the same graph G, in this case we have got clique and another possibility, and you can see that NC1 equal to 3 and NC2 is equal to 4. Therefore, you can say NC2 is more than NC1.